Imagine, if you will, not a physical road, but this vast, invisible highway stretching across, well, everywhere. Our cities, our skies.
Right.
This isn't tarmac we're talking about. It's the radio frequency spectrum. It's the silent, essential backbone of our entire wireless world.
Absolutely. Everything runs on it.
Everything. It's where your Wi-Fi lives, where your phone calls travel, where, streaming videos, Zoom, countless smart devices communicate. But here's the thing, the critical challenge we're facing today,
Hmm.
this invisible highway. It's getting incredibly congested.
Gridlocked almost.
Exactly. We're quite literally running out of room for new devices, for groundbreaking applications, and for all the new ways you want to connect.
It's a classic resource management problem, isn't it?
Right.
We've historically treated this wireless spectrum like plots of land in a city.
Yeah, that's a good analogy.
Once a plot is assigned, it's considered taken, right? Regardless of whether the building on it is always bustling or, sits empty most of the time.
Right. The lights might be off 90% of the time.
Precisely. And the static allocation has led to a situation where nearly all usable spectrum is technically owned, even if large portions of it are actually idle for significant periods.
Okay, so it's allocated but not always used.
Exactly. But what if we could make this system dynamic? What if our wireless devices could intelligently find and utilize those empty airwaves, much like a savvy driver navigating open lanes on a highway during off-peak hours?
Ah, okay. Like ways for radio waves.
Oh, sort of, yeah. That is the audacious transformative promise of cognitive radio, or CR.
Cognitive radio. Okay. And for CR to really deliver on that promise, for your devices to become these savvy drivers, they need a fundamental superpower: spectrum sensing.
That's the core of it.
This isn't just about detecting a signal. It's about meticulously scanning, understanding which parts of this invisible highway are currently unused by their licensed or primary users.
The owners of the lanes, basically.
The owners, right, the ones who nominally own these lanes. It's the eyes and ears of a cognitive radio system, a foundational and pretty complex challenge that frankly makes or breaks the entire CR concept.
It really does. Without effective sensing, these systems they can't exist. They can't be polite neighbors.
Delight neighbors, I like that.
Precisely. And today, for this deep dive, we're going to unpack a really interesting paper by Kamal Captain. It's titled Cooperative Wideband Spectrum Sensing Under Reporting Channel Errors, Analysis and Algorithm.
Okay, quite a title.
It is, but our mission is to understand how cognitive radio devices are trying to solve this critical bottleneck. We'll explore the sophisticated techniques of cooperative wideband spectrum sensing, or CWSS.
CWSS, got it.
Which is essentially about multiple devices working together, pooling their information to get a clearer picture of the wireless environment.
Strength in numbers.
Exactly. Then, we'll zero in on a hidden yet absolutely crucial hurdle that has often been overlooked in research: imperfect reporting channels.
Imperfect reporting. Wait, what does that mean? Like the messages get messed up?
Precisely. What happens when the very information you need to make smart decisions gets garbled or lost in transit? And finally, we'll discover a clever yet surprisingly elegant solution proposed in this paper that dramatically improves reliability.
Okay, so sensing, cooperating, the problem of garbled messages, and a clever fix. Sounds like a journey.
It is.
And understanding this isn't just for the engineers or wireless gurus tuning in. This deep dive is really about the fundamental plumbing of our digital world.
It impacts everyone.
It really does. It's about how we unlock more efficient wireless communication, leading directly to faster, more reliable connections for you. Whether you're streaming 4K content, doing a critical remote work meeting, or exploring smart home tech, IoT devices.
All that stuff.
This is the unseen innovation working behind the scenes, making it all possible or more possible.
Making it work better.
Right. So let's unpack this, starting with the fundamental why behind cognitive radio. Why is this even a problem we need to solve? The paper immediately highlights what it calls the bottleneck of wireless communication.
That's right. And the core information here is, well, it's quite stark. The sheer exponential increase in wireless applications, think smartphones, smartwatches, connected cars, VR, all demanding more and more bandwidth.
It's insatiable.
It really is. And that, coupled with the traditional static way we've allocated spectrum, has led to a genuinely scarce radio frequency, or RF, spectrum. It's a system designed for a different era, basically.
An emptier era.
Definitely. Fewer devices, simpler uses. Imagine an interstate highway built for, horse-drawn carriages, suddenly needing to accommodate millions of high-speed cars. Almost all available spectrum is already allocated or licensed.
So the plots are all taken.
Pretty much. Creating a severe limitation for developing new wireless technologies, new applications. This truly is a bottleneck for future innovation and growth in the wireless space.
It really is like that city analogy we used. Every single plot of land is owned, assigned, often permanently. Even if that building sits empty most of the time, that plot is still considered taken.
Unavailable.
Unavailable. So when a new business or a new kind of wireless service wants to open, there's literally no space for it to operate. It's this paradox. Huge, ever-growing demand for wireless services, but a seemingly finite, fully booked resource.
And this leads us to the aha moment that the paper really brings out.
Yeah.
The hidden opportunity. It's lurking in those underutilized airwaves.
Hidden opportunity, because they're allocated but empty sometimes.
Exactly. And this isn't just theoretical. Measurements conducted by the Spectrum Policy Task Force, SPTF, of the FCC here in the U.S., have actually shown that many licensed bands are free most of the time and are significantly underutilized.
Wow. So it's not that the airwaves are always full.
Not at all. It's that they are often empty, yet legally inaccessible because of that static allocation.
That's truly fascinating and, yeah, a bit frustrating when you think about it. So the problem isn't necessarily a physical lack of spectrum itself,
Well, no, the physics are the same.
but rather an inefficient, almost wasteful management of it.
That's the key.
It's like realizing that while our highways are absolutely gridlocked during rush hour, those very same lanes are completely empty overnight, or even for large parts of the day in certain areas.
Exactly. There's this hidden, untapped capacity there just waiting to be intelligently utilized. The source clearly states this is due to static spectrum allocation leading to wastage of the radio resources.
Can you give some examples of this wastage? Like what kind of bands are we talking about?
Oh, sure. Think about emergency services radio bands. They are absolutely critical, so they're allocated exclusively to, say, police or fire departments.
Right, you need those clear.
Definitely. But they're not in constant use 24/7. When there's no emergency call going out, those frequencies are completely silent. Dead air.
Okay, makes sense.
Or consider TV broadcast bands. Especially with the big shift to digital and streaming, many of those older analog TV channels, or even some digital ones in certain areas, are now underutilized.
Yeah.
Sometimes completely vacant geographically.
Right, the so-called TV white spaces.
Exactly. And then you have things like specialized radar or military frequencies. They might only be active for short bursts or in very specific locations. Under a static allocation model, all these crucial yet intermittently used airwaves remain locked up.
Creating these digital deserts of unused bandwidth, even right next to overloaded frequencies.
That's the wastage. We're talking about valuable wireless real estate just sitting idle because the rules say it's taken.
So this is where cognitive radio CR steps in as that dynamic solution. It's not just a technological tweak, it's a fundamental paradigm shift.
It really is a different way of thinking about spectrum.
The paper defines CR as a promising approach that allows unlicensed users, also known as secondary users,
Big guess?
to use the bands allocated to licensed users known as primary users
The owners.
when they are not in use. That's the crucial bit. When they're not in use,
Opportunistic access.
it means moving away from a rigid, first-come, first-served, permanently assigned model to a much more flexible, intelligent, efficient system. And it's not just an academic idea. The paper notes many countries have actually modified their spectrum usage policies to enable this.
Regulators are catching on, slowly but surely.
But what are the biggest hurdles to widespread adoption? I mean, beyond the tech challenges we're about to dive into, is it just policy?
That's an excellent point.
Mm.
While the technical challenges are significant, the regulatory and frankly political hurdles are equally, if not more, complex.
Ah.
Historically, spectrum has been allocated by governments through licensing, often in very large exclusive blocks, and that generated substantial revenue.
Right. Auctions and fees.
Exactly. Shifting to a dynamic model fundamentally challenges that established system. There's a natural reluctance from incumbent primary users to the owners to share. They worry about potential interference or maybe just a perceived loss of control over their dedicated spectrum.
I can see that. If you paid billions for a license.
Precisely. Imagine telling a railroad company they now have to share their private tracks with local delivery vans.
Yeah.
Even when the trains aren't running, there'd be pushback.
Yeah, okay.
So building trust, establishing clear liability frameworks, who pays if interference does happen,
Mm-hmm.
and creating a unified regulatory approach across different countries and regions. These are massive undertakings.
So the tech might be ready, but the framework needs to catch up.
In many ways, yes. The paper acknowledges these shifts in policy are happening, but implementing them broadly requires immense collaboration between governments, industry, and researchers like Kamal Captain.
That context really helps frame the challenge. But as we mentioned, at the heart of making this dynamic allocation work, whether it's for finding space near an emergency band or a TV channel, hinges on one crucial capability: spectrum sensing.
It all comes back to sensing, the eyes and ears of cognitive radio.
Indeed. The primary task of a cognitive radio, its moment-by-moment job, is precisely this. Secondary users need to dynamically find out the unused PU's frequency bands.
Constantly scanning, listening for those quiet pockets.
But it's not just about finding open spots. There's that critical second part, the polite neighbor rule. Secondary users also need to vacate the PU bands whenever the PU starts using its frequency bands.
Immediately. No hesitation.
To minimize any interference, this isn't optional. It's a strict requirement. You can't disrupt critical services or other legitimate users.
And to do this reliably, especially quickly, requires incredibly powerful spectrum sensing techniques.
So it's not just finding a parking spot, it's being ready to instantly move your car, like the second the owner even thinks about pulling up.
That's a great way to put it. A delicate, high-speed balancing act.
The paper notes that a technique called energy detection, ED, is quite popular for this. Why? Because of its simplicity and ease of implementation and its blind nature. What exactly does blind nature mean here, and why is that such a huge practical advantage?
Blind nature is a really important characteristic for practical CR systems. It means the secondary user doesn't need any prior knowledge about the primary user's signal.
Ah, okay. It doesn't need to know what language the owner speaks.
Exactly. It doesn't need to know the primary user's modulation type, power level, specific coding, protocol. None of that detail. It simply listens for energy, for any sound on a given frequency.
If it hears something, it assumes someone's there.
Pretty much. If there's significant energy, it assumes the channel is occupied. If it's quiet, below a certain threshold, it assumes it's free.
And the advantage?
It's huge because in a real-world scenario, a cognitive radio might encounter many different types of primary users, TV broadcasts, radars, mobile networks, you name it. It would be practically impossible for it to have pre-programmed knowledge about all of them.
Like needing a universal translator for every possible signal type.
Exactly. Energy detection bypasses that by simply asking, is there any energy here? Yes or no? Its simplicity makes it fast and cheap to implement, which is absolutely vital for widespread adoption in everyday devices.
That makes perfect sense. Simplicity is often key to scalability. And this leads us to the scale of the challenge, moving to wideband sensing. Because primary user occupancy is often sparse.
Meaning lots of little gaps.
Right, meaning there are many spectrum opportunities scattered across a broad range of frequencies. It's essential to design powerful wideband spectrum sensing WSS techniques. They need to search for spectrum opportunities over a wide frequency range.
Absolutely. If narrowband sensing is like checking one specific street for an empty parking spot.
Which might take forever if that street is full.
Right. Then wideband sensing is like checking an entire city block, or maybe even the whole city, all at once, to find any available parking.
Okay, much bigger task.
The sheer scale involved significantly increases the complexity because you're dealing with vastly more data simultaneously. And that brings us to how these CR users actually sense this vast dynamic landscape, specifically through cooperative wideband spectrum sensing. How do we tackle this massive data problem?
The challenges of wideband sensing are indeed significant. The paper highlights that traditional WSS methods, using something called Nyquist sampling. That sounds familiar.
It's a fundamental signal processing concept.
Right. They require a very high sampling rate, which can be practically demanding. Can you elaborate on why a very high sampling rate is such a practical hurdle for devices like my phone?
Of course. Think of sampling rate like taking pictures of a fast-moving object. If you take too few pictures per second, the image will be blurry, you'll miss details, right?
Right, motion blur.
To accurately capture a wide range of frequencies, which means potentially lots of different signals or sounds happening simultaneously across that wide band, you need to take an incredibly large number of snapshots per second. That's a very high sampling rate, dictated by the Nyquist theorem for the entire wide band.
And more snapshots means?
It translates directly to expensive and power-hungry hardware. Your device needs extremely fast analog-to-digital converters, ADCs, massive processing power, and a lot of memory just to handle all that incoming data in real time.
Okay, so battery drain, cost, complexity.
Exactly. For a small battery-powered device like a smartphone or an IoT sensor, Sampling the entire wideband at the full Nyquist rate is often just not feasible today. It's too demanding.
So are there workarounds? The paper mentioned compressed sensing.
Yes, compressed sensing CS algorithms aim to alleviate this. They try to sample at sub-Nyquist rates, meaning taking fewer but hopefully smarter snapshots. The idea is to exploit the fact that the spectrum is often sparse, mostly empty.
Ah, okay. So you don't need to sample the emptiness so much.
That's the intuition. Yeah. But the catch is that these CS algorithms themselves are mathematically sophisticated, and their implementation is also expensive and complex. So the trade-off often becomes high cost versus high complexity. There's no easy win there.
So it's a practical hurdle either way. The sheer volume of data in wideband sensing can be overwhelming, making simple and efficient solutions absolutely paramount. You can't just throw more bandwidth and processing power at it without hitting a wall.
This is precisely where the paper introduces a rather clever optimization. Partial band Nyquist sampling, PBNS.
Partial band. Okay, so not the whole thing.
Exactly. The core insight here is genuinely brilliant and practical. Secondary users may not be interested in finding all the spectrum opportunities.
Right, like your parking analogy. I don't need to know about every empty spot in the city, I just need one nearby.
Precisely. The interest lies in finding sufficient numbers of spectrum opportunities, enough to meet the user's current need. So, PBNS samples only a part of the wideband, maybe a few selected channels, thus significantly reducing the sampling rate.
That's a truly brilliant move. It's recognizing that a good enough solution is often far more practical, efficient, and cost-effective than striving for absolute perfection, especially when perfection comes with that huge price tag and complexity and resources.
It's pragmatic engineering.
The paper gives a great example. Imagine a wideband of D10 channels, like 10 lanes on a highway. PBNS might filter out and only sense, say, LT6 specific channels. That significantly reduces the processing load, the sampling rate requirement, while still giving you plenty of opportunities to find an open lane. It's targeted efficiency.
Exactly. And then we combine this targeted sensing with the power of many eyes through cooperative sensing.
Ah, the CWSS part.
Right. The paper focuses on a centralized approach with multiple distributed cooperating secondary users, CSUs, and a fusion center, FC.
Okay, break that down. CSUs and an FC.
Think of the CSU's cooperative secondary users as distributed scouts on the ground. Each one does its own local sensing, maybe using that PBNS approach we just discussed.
Yeah.
They take local measurements and make initial decisions about spectrum availability in their vicinity.
Okay, individual scouts reporting in?
Then they send their final result, their local finding, to the FC, the fusion center. That's the central command post. The FCC gathers reports from all the scouts and takes the final decision about which channels are truly free across the area.
And the benefit.
This approach, crucially, takes advantage of spatial diversity.
Spatial diversity. It's intuitive, isn't it? Just as a single person might miss a subtle detail, a whole team of observers can provide a much more robust, accurate picture, especially in a dynamic environment like the wireless spectrum. Can you explain spatial diversity using our scouting team analogy?
Yeah, think of it like this. If you send one scout to check for an enemy, they might be in a bad spot, maybe behind a building, or in a valley where the signal is weak. They might have a poor line of sight, or just misinterpret what they see due to local interference or fading.
One beta point isn't always reliable.
Exactly. But if you send 5 scouts to different vantage points observing the same area, they're far more likely to get an accurate picture collectively. One scout might be blocked by a hill, deep fade.
Yeah.
Another might be too far, path loss. Another might have local noise. But if multiple scouts report seeing nothing, or if several independent scouts report seeing something, your confidence in that observation goes way up.
Okay, so each CSU is in a slightly different physical location.
Right. They experience different fading conditions, different interference levels, different line-of-sight paths to the primary user signal, if it exists. By combining their independent observations at that central fusion center, you average out those individual imperfections, those local blind spots.
And you get a far more reliable, accurate overall picture of which parts of the spectrum are truly free and which are occupied.
It's strength in numbers, applied directly to wireless sensing, mitigating the impact of unlucky locations.
And those individual scouts, the CSUs, have their own local enhancements too, right? Making their initial observations even stronger before they even report in.
Yes, the paper details that. CSUs are often equipped with multiple diversity antennas.
Multiple antennas on each scout.
Correct. This allows them to benefit from both space diversity, slightly different antenna positions, and antenna diversity, right there at the local device. They use a technique called square law, combining SLC diversity, to combine the signals received from these different antennas.
Okay, SLC, what does that do?
It essentially takes the energy detected by each of those multiple antennas for a specific channel. It squares the signal strengths from each antenna, which emphasizes the stronger signals and diminishes weaker noise, and then simply adds them all up.
We square it.
Squaring makes all values positive and gives more weight to stronger signals. It's a common way to combine energy from different branches non-coherently. This whole process helps to mitigate the effects of fading and noise that might impact just one antenna, giving the CSU a clearer, more reliable initial reading of how much energy is present on that particular channel.
So it's like getting a better local measurement by using multiple ears.
Precisely. Getting the clearest possible local picture before making a decision. After getting this combined energy measurement, the decision statistic, for each channel in its partial band, the CSU then performs ranked channel detection, RCD.
Ranked channel detection,
Yeah.
RCD. So they rank the channels they looked at.
Exactly. They effectively create a ranked list. They arrange the channels they sensed based on that decision statistic, basically, how empty or quiet each channel seems. The quietest channels, the ones with the lowest energy, are at the top of the list. The noisiest are at the bottom.
And why rank them? Why not just report all the ones below a certain energy level?
Good question. Instead of trying to make a hard decision free-busy on all the sense channels, which can be prone to error, especially near the decision threshold, they decide to focus their report. They only report on the top XI channels, say, the top 2 or 3 quietest ones they found.
Ah, so they report the most likely candidates for being free.
Exactly. It's another layer of efficiency and robustness. It ensures that only the most confident local free channel detections are passed on to the fusion center. It's about quality control at the source, reducing the amount of potentially marginal information sent upstream.
Okay, so even before the information gets to the central fusion center, there's a lot of sophisticated local intelligence happening at each CSU, multiple antennas, SLC combining, ranking the results, all designed to make that initial measurement as robust and efficient as possible.
Absolutely. It really shows how each local piece contributes significantly to the overall cooperative strength of the system. It's not just dumb sensors reporting raw data.
Now, we've talked about how smart these systems are, how they cooperate, how they optimize locally, but here's where it gets really interesting and where this paper by Kamal Captain identifies that critical, often overlooked vulnerability, the hidden problem of imperfect reporting channels.
This is the core contribution of the paper, I think.
You'd think the sensing itself is the hardest part, right?
Yeah.
Getting that initial reading correct.
That's the assumption many researchers have made, and it's a crucial point the paper challenges directly. While a lot of previous work in this field assumed error-free reporting channels between those cooperative secondary users, the CSUs and the Central Fusion Center.
Like a perfect noise-free connection back to base.
Exactly. The paper very realistically points out that in real life, these reporting channels are affected by phenomena such as fading and shadowing, leading to imperfect reporting channels.
So the connection back to the FC isn't perfect, it's noisy.
It's a wireless channel itself, usually, subject to all the same problems as any other wireless link. This means the communication link between the collaborating devices and the central brain of the system is often far from perfect.
That's a real eye-opener. It means the very act of cooperating, of sending those reports back to Central Command, introduces a new, unforeseen point of failure.
A vulnerability introduced by the cooperation itself.
It's like our scouts from earlier trying to send their critical reports back over walkie-talkies riddled with static, or through areas with poor reception.
Yeah,
A
exactly.
message like, Channel 3 is clear, could easily become corrupted into Channel 4 is clear, or Channel 8 is clear, just due to noise on that reporting link.
And if the central command, the fusion center, gets corrupted information, well, even the best local sensing in the world won't prevent the system from making a bad decision.
Right. This system is only as good as its weakest link, and that link often turns out to be the communication between the sensing units. This could have tangible, damaging effects on performance, like telling a user a channel is free when it's actually occupied by the primary user.
Or telling them a channel is busy when it's actually free, wasting an opportunity.
Yeah.
Both are bad outcomes.
The paper then goes a step further and actually quantifies this degradation. It provides a rigorous mathematical framework to understand the problem properly.
Which is essential for designing solutions.
It proposes a specific reporting channel model under erroneous reporting. It's characterized by a probability, P, that a transmitted channel number is received corrupted.
P is the error probability on that reporting link.
And when a number is corrupted, the model assumes it's detected as any other of the L1 possible channel numbers with equal probability. So a 3 could become a 1, 4, 4, 5, etc. randomly.
It's a standard way to model these kinds of errors simply.
This model allows them to precisely measure the impact, and the analysis definitively shows that the performance of CWSS is greatly affected by the reporting channel errors.
It's not a minor effect. It's significant.
So it's not just a theoretical concern, it's a measurable, practical problem that significantly impacts the real-world performance of these systems. And the numbers don't lie. The paper gives some stark examples. Can you walk us through one of those numbers, maybe from Table 2, and help us understand the real-world consequence for us, the users?
Absolutely. The data from Table 2 is particularly illuminating. It really drives the point home. Imagine a scenario where the system is designed to maintain a certain level of protection for the primary user. Let's fix the probability of excessive interference to primary users, or PEIO, at a low acceptable level, say 0.07.
Okay, so we're being very careful not to bother the owner. 7% chance of messing up.
Right, a low interference target. Now, if there are no reporting errors at all, a perfect reporting channel, meaning P is 0.0, the system achieves a probability of insufficient spectrum opportunity, or PIAS, of 0.1587.
PISO, so that's the chance of the secondary user not finding a free channel when they need one.
Exactly. So about a 16% chance in this ideal case, the system is doing a reasonably good job of finding available channels for the secondary users, the guests.
Okay, 16% seems okay, but what happens when the reporting channel gets noisy?
Here's the kicker. The moment you introduce even a moderate level of reporting error, say P is 0.3, meaning about 30% of the reported channel numbers get corrupted in transit between the CSU and the FTC.
Which doesn't sound impossibly high for a wireless link.
Not at all. Could easily happen. That PSU shoots up dramatically to 0.241.
From 0.1587 to 0.241.
That's a big jump. What's the percentage increase?
It's a staggering 51.85% degradation in finding those precious spectrum opportunities.
Wow. Over 50% worse performance just because the messages got garbled. Exactly. To put it in relatable terms, for you, the user, a bit of communication noise between the cooperating devices, like static on that walkie-talkie link, can effectively cut your available wireless bandwidth or connection reliability by over 50%.
Just because the system can't accurately figure out which lanes are open anymore?
Right. The information about the open lanes got corrupted. It's like having half the available parking spaces disappear from your map because the signal telling you they were open got scrambled. That's the real-world impact the paper quantifies purely because the reporting data got messed up.
Okay, that degradation is huge. And that's why the paper introduces these new, more relevant performance metrics specifically for wideband sensing, different from the traditional narrowband metrics like PF, false alarm, and PN detection probability.
Yeah, those don't quite capture the goal here.
For wideband spectrum sensing, they use PISO, probability of insufficient spectrum opportunity, defined as PRS-SD, where S is the number of successfully identified O-off-F channels.
The number of free channels we actually found.
And SD is the required number of spectrum opportunities.
How many channels the secondary user actually needs right now?
So if S is less than SD, it means you, the user, aren't getting enough available bandwidth when you need it.
Right. You might experience frustrating buffering during your video stream, significant slowdowns in downloads, or your smart thermostat just won't connect reliably to the network. It's a direct measure of how well the system serves secondary users. Does it find you a spot when you need one?
Exactly. And the second critical metric is PEIO, probability of excessive interference to primary users. That's defined as PRIID.
Okay, what are I and AD?
Here, I is the number of missed on channels, meaning a primary user was actively using that frequency, but our system mistakenly thought it was free and allowed a secondary user to jump on.
Oops. The cardinal sin of cognitive radio.
Pretty much. And N is the allowed interference, the maximum number of times we can make that mistake, which is typically set very, very small, like maybe 0 or 1.
This one is paramount because it directly relates to our polite neighbor rule. If PEIO is too high, your device might jump onto a channel that's already in use, causing interference to a critical service.
Like an emergency broadcast, air traffic control, or just someone's important phone call.
You absolutely cannot let that happen often. The paper explicitly states, the desirable values of PISO and PEIO are application-dependent and always selected by setting a fair trade-off between these two.
A trade-off. You can't perfectly optimize both.
Generally not. If you become extremely cautious to avoid interference, low PEIO, you might miss out on some genuine opportunities, higher PISO. If you're aggressive in grabbing spectrum, low PISO, you risk causing more interference, higher PEIO.
So engineers have to balance. The paper says for sensitive information, PEIO must be as small as possible. Makes sense. And for time-sensitive data, like maybe VoIP or gaming, PISO must be very small. You need that bandwidth now.
Exactly. It highlights the critical engineering balancing act. Find enough spectrum for the guests without stepping on the owner's toes, especially when those owners have priority access and might be running critical services.
And that brings us, finally, to the paper's clever solution. Repetition code-based CWSS, or RCCWSS, it addresses this critical vulnerability of imperfect reporting channels in a, well, you called a surprisingly elegant way.
It really is. When you hear the words repetition code, it almost sounds too simple for such a complex problem.
Yeah, just repeat stuff. How does that help?
It is simple in concept, and that's truly its beauty and ingenuity here. They draw inspiration from a very fundamental concept in communication theory, the repetition code.
Okay.
This is one of the simplest error-correcting codes out there, but it's incredibly effective when applied smartly in the right context. The core concept is straightforward. The message to be transmitted is repeated several times before transmitting.
Like shouting, fire, 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 instead of just fire.
Exactly. To make sure the message gets through, even if someone mishears one of the words due to noise. Then, the receiver applies a majority decision rule to recover the message.
Okay, so majority vote. Let's try our walkie-talkie analogy again. If a CSU wants to report channel 1 is free, and the repetition length, let's call it R, is 3,
A common small value to start with.
it sends 111. Now, if the Fusion Center receives 121 due to noise on the reporting channel,
One of the ones got flipped to a 2.
the majority rule sees 2 1s and 1 2, so it correctly interprets the message as 1.
That's the brilliance. The error got corrected.
But what if it receives 1 2 2, maybe 2 errors happened?
Then the majority rule would see 1, 1, and 2 2s, and it would wrongly detect 2. So it's not foolproof, especially if the error rate is very high or errors happen in bursts.
Okay, so it doesn't solve everything, but it significantly tips the odds in favor of correct reception, especially for random errors.
Exactly. It's about statistical improvement. It makes errors much less likely, especially if the errors are random and somewhat isolated. For example, if your scout reports channel 5 clear, channel 5 clear, channel 5 clear, and command hears channel 5 clear, channel 4 clear, channel 5 clear, the system correctly understands channel 5 because it appeared twice.
It provides redundancy to overcome that intermittent noise. Simple, but effective.
Very.
So how does this RCCWSS actually function in practice within the larger system? How does it combine with the PBNS and the ranking and everything?
Okay, let's walk through the flow. It starts with the cooperative secondary users, the CSUs. Each CSU first performs its local processing, just as we discussed before.
Right, the PBNS to select channels, the multiple antennas, the SLC combining to get the energy statistic.
Exactly. And then they perform rank channel detection on those XD channels to identify the most promising locker-free channels. That's the quality control at the source.
Okay, same initial steps.
The critical new step in RCWSS happens next. Each CSU then reports the free channel numbers, those top XD candidates, to the FC by repeating them R time.
Ah, so the repetition happens after the local ranking.
Yes. So if a CSU identifies channels 5 and 7 as its top 2 free candidates, and the repetition length R is, say, 3, it transmits the sequence 555777 over that potentially noisy reporting channel to the Fusion Center.
Okay, sends the repeated list.
The Fusion Center, on its end, receives this potentially corrupted sequence. For each block of R repetitions, like the 3 5s, then the 3 7s, it applies that majority rule to decide which number was transmitted.
So it cleans up the received message first using the majority vote.
Precisely. It does error correction before combining reports from different CSUs.
Yeah.
After this error correction step for each report from each CSU, the FCC then proceeds as usual. It counts the total number of times a particular channel, the channel 5, is reported free across all the cooperating CSUs.
It makes the final decision based on that threshold of day.
Exactly. If channel 5 was reported as free by at least FD CSUs after error correction, the FEC declares channel 5 officially available for secondary use. It's a comprehensive, layered approach to robustness.
So it's this clever integration of robust local sensing, cooperative reporting with repetition, and this elegant error correction at the Fusion Center that creates a significantly more robust system. Figure 4 in the paper actually provides a concrete example, walking through this whole process visually.
Yeah, it shows the reports going out, getting corrupted, then being decoded by majority vote at the FEAC before that final tally and decision.
Yeah.
It really ties the whole system together nicely.
And the proof, of course, is in the performance numbers. The RCCWSS algorithm demonstrates truly significant advantages, which is why this paper is so important.
The result's quite compelling.
First, it can reduce reporting channel errors to a great extent. But here's the really powerful part. The paper shows that by increasing the repetition length R to a certain value, the algorithm performs as if there are no reporting channel errors.
Think about that. It basically overcomes the channel noise entirely from a performance perspective.
That's incredible. A relatively simple technique based on repeating information can effectively eliminate a major source of system degradation. It's like turning that noisy walkie-talkie channel into a perfectly clear fiber optic line just by strategically repeating the message enough times.
For practical purposes, yes.
Figure 10 in the paper dramatically shows this. It plots performance curves. With p equals 0.2, which is a significant error rate, 20% corruption.
A pretty noisy channel.
RCCWSS with a repetition length R equals 7 achieves almost the exact same performance curve as the ideal PBNS-CWSS algorithm, the one without repetition coding, operating with no reporting channel errors at all. P is 0.
The lines basically overlap.
That's not just an improvement, that's a massive leap in practical reliability. It effectively closes that vulnerability we identified.
It makes the cooperative system robust to the very channel it relies on for cooperation.
Furthermore, the paper rigorously demonstrates that RCCWSS outperforms recently proposed PBNS-CWSS without repetition, OA-CWSS, and 1-bit FFT-CWSS algorithms when those reporting errors are present.
Which they usually are in real life. This is a key finding, establishing RCCWSS as a superior approach for practical wideband sensing in the presence of reporting errors.
This is where the numbers truly speak for themselves, illustrating the dramatic impact. Let's look at Figure 7 and Table 3 again. They compare algorithms under the same conditions with reporting errors, p 0.2.
Right.
For a target PEIO probability of interfering with the primary user of 0.04, RCCWSS, with R7, achieves a PISO probability of not finding a channel of 0.1814.
Okay, about 18% chance of not finding a spot.
Now compare that to the others. The original PBNS-CWSS, without repetition, under the same noisy conditions, gets a PISO of 0.2193.
So RCCWSS is already better, about 20.89% better PISO.
But look at OA-CWSS. Its PISO is 0.4389.
Wow, that's much worse. Almost a 44% chance of not finding a channel.
Compared to that, RCCWSS is 58.66% better. That's a huge difference in usability for the secondary user.
Massive.
And 1-bit FFT-CWSS is at 0.3368 PSO. RCCWSS is still 46.14% better than that.
So this repetition code approach consistently delivered dramatically better results in finding available spectrum for you, the user, under realistic noisy reporting conditions, sometimes by more than 50% improvement.
It's not just incremental. It feels like a paradigm shift in reliability for these systems, making them far more practical for real-world deployment.
And the paper explains why this dramatic difference exists, particularly compared to OA-CWSS and 1-bit FFT. Those algorithms are designed to decide on all the channels in the frequency band of interest.
They try to classify every single channel.
Yes. While this might sound comprehensive, it increases the overall probability of making an error somewhere and thus potentially causing interference or missing an opportunity. RCCWSS combined with the PBNS focus on just finding the required number of spectrum opportunities, its TISD, and its integrated error correction.
It's more targeted and more robust.
Exactly. It's simply more efficient and precise at identifying usable spectrum without taking unnecessary risks on channels it doesn't strictly need to classify. It's smarter about what it's looking for and more resilient to errors when recording its findings.
And the paper doesn't stop there. It also dives into the impact of various design parameters on the performance of RCCWSS itself. This is crucial for practical implementation for engineers designing these systems.
Understanding the trade-offs.
Right. Let's talk about the repetition length, R, first. How does simply repeating the message more times affect performance, and what are the trade-offs involved?
A fantastic question, and it's a key design choice. As the repetition length R increases, the performance, specifically the PISO, finding opportunities, dramatically improves, especially when reporting errors are high.
More repeats, better error correction.
It's intuitive. The more times you repeat a message, the higher the chance the majority vote gets it right, even with significant noise. For instance, Table 4 and Figure 9 show that increasing R from 3 to 7 reduces piezo by nearly 24% for a fixed PEIO of 0.025. That's a solid gain.
But there must be a downside. Why not just repeat 100 times?
The trade-off is overhead. More repetitions means sending more data over that reporting channel. This consumes more bandwidth on the reporting link itself, takes more time, and requires more processing power at both the CSU to send and the FC to decode.
So it costs energy and time.
Exactly. This is why the paper even suggests an adaptive R based on the measured quality of the reporting channel shown conceptually in Figure 15. The idea is the system could be even smarter.
Only repeat more when the line is really noisy.
Precisely. Use R3 if the channel is clear, maybe jump to R7 or R9 if it gets bad. Save resources when you can, add robustness when you need it. It's about being smart with your redundancy.
That makes perfect sense. Dynamic adaptation. Okay, another key parameter, the fusion-centered decision threshold, FDD. This sounds like it directly impacts that polite neighbor rule, the PEIO.
You're spot on. FT is the number of times a channel must be reported free by different CSUs after error correction before the Fusion Center declares it genuinely available.
So how many scouts need to agree it's clear?
Exactly. Increasing FDU significantly improves performance in terms of safety, providing more security against interference to the PU. It makes the Fusion Center more conservative, more skeptical. It demands more consensus from the scouts before allowing a secondary user onto a channel.
More votes needed, less chance of a mistake causing interference.
Right. For a fixed PEIO target of 0.06, Table 5 and Figure 11 show that increasing F from 1, just one CSU needs to say it's free, to 3, need consensus from 3 CSUs, reduces the resulting piezo by over 20%.
Wait, increasing FDI reduces piezo? That seems counterintuitive. Shouldn't being more cautious make it harder to find channels?
That's a subtle but important point in how these metrics interact, especially in the plots. When we fix the PEIO, the interference probability, increasing FDI makes the system inherently safer. To maintain that same low PEIO with a higher FDI, the system can actually afford to be slightly less sensitive overall at the local CSU level, adjusting local thresholds implicitly. This combination can sometimes lead to finding more reliable opportunities that meet the strict interference constraint. It's about optimizing the entire system to meet the PEIO target. A higher FDA provides more robustness against individual CSU errors, making it through the fusion process.
Okay, so a higher heft allows the system overall to operate more reliably at a specific low interference target, which can sometimes mean identifying the truly safe opportunities more effectively. It's a system-level optimization.
Precisely. It gives you more confidence in the free decisions. The potential consequence, if you push FD too high without adjusting other parameters, could be a higher piezo eventually as you become overly cautious. It's a direct control knob for that critical balance between finding opportunities, PISO, and avoiding interference, PEIO.
Got it. Then there's the number of partial band channels, L. We talked about how PBNS selects a subset of channels to sense out of the total wideband D. What happens if you increase L, the number of channels in that partial band being sensed?
Increasing L generally improves PISO, the probability of finding enough spectrum. It's fairly straightforward. If you're searching a wider swath of the spectrum, L is larger, you're simply more likely to stumble upon available free channels.
More places to look, higher chance of finding something.
Exactly. If you're looking for parking spots in 6 blocks, L6, versus just 2 blocks, L2, you're more likely to find one. Table 6 and Figure 12 show this. Increasing L from 2 to 4 reduces piezo by nearly 25% for a fixed PEIO of 0.1.
But again, the trade-off.
Yeah. Like repetition length, there's a trade-off. Sampling more channels, L, increases the computational load and energy consumption at each CSU. They have to sense and process more data locally. It's about finding that sweet spot. Sense enough channels to have a good chance of finding opportunities, but not so many that you overtax the capabilities of the local devices.
Makes sense. And what about the physical hardware, the diversity branches
Hello.
at the CSUs, those multiple antennas we mentioned earlier? How much do they really impact the overall cooperative system performance?
The diversity branches, those multiple antennas at each individual CSU, are critically important. They provide robustness right at the source of the measurement. More diversity branches significantly improve performance, especially under challenging environmental conditions like Nakagami fading, which is a common statistical model for signal degradation in wireless channels.
So multiple local antennas really help cut through the noise.
Definitely. Table 7 and Figure 14 show a stark difference. For a fixed PEIO of 0.06, the PISO achieved with Peagle's 4 diversity branches is almost 50% smaller than with only P1, a single antenna.
Wow, 50% better PISO just from adding more antennas locally.
Yes, it highlights the importance of robust local sensing before any information is even reported cooperatively. If each scout can get a much clearer initial picture of its immediate surroundings by listening with multiple ears, using SLC combining effectively, then the information that sends to headquarters is already much more reliable.
Garbage in, garbage out. But good data in, better decisions out.
Precisely. Better local data leads to a more accurate final decision for the entire cooperative system.
And finally, a classic factor in any wireless system, signal-to-noise ratio, SNR. This measures how strong the primary user signal is, if present, compared to the background noise floor. How does higher SNR play out here?
As one would absolutely expect, higher SNR dramatically improves performance. When the signal you're trying to detect, the PU signal, is much stronger than the background noise, it's simply easier to tell if it's there or not.
Less chance of mistaking noise for a signal or missing a weak signal in the noise.
Exactly. Figure 13 illustrates this perfectly. For a fixed PEIO target of 0.04, the PISO achieved at an SNR of 0 dBB is over 85% smaller than the PISO at -10 dB SNR. That's a huge improvement in finding opportunities when the signal conditions are better.
So good signal quality is fundamental.
It's the foundation upon which all these clever cooperative and error correction techniques build. Better signal quality means fewer errors in the initial sensing phase at the CSU, and potentially fewer errors on the reporting channels too, though they are separate channels. It all translates directly to more accurate sensing, which means more available spectrum found reliably for you, the end user.
So we started this deep dive imagining that vast, invisible wireless highway and quickly realized it was becoming incredibly congested due to, well, old habit static allocation.
Lock up resources.
We then explored the ingenious concept of cognitive radio, this dynamic solution designed to smartly find and utilize those underutilized airwaves, transforming them into valuable, usable bandwidth when the owners aren't using them.
Unleashing trapped capacity.
We zoomed in on the intricate mechanics of cooperative wideband spectrum sensing, CWSS, seeing how multiple devices could work together like a smart scouting team to map out the spectrum landscape much more reliably than any single device could alone.
Using techniques like PBNS and leveraging spatial diversity.
And then we uncovered that critical, often hidden flaw, the imperfect reporting channels, the potentially noisy links between those collaborating devices and the central decision maker.
The Achilles heel of cooperation sometimes.
A significant vulnerability that, if ignored, could severely degrade the entire system's performance and diminish the very benefits cognitive radio promises. But, as we saw from Kamal Kaptan's paper, the elegantly simple concept of repetition codes,
Just repeating the message.
applied in a sophisticated way within the RC-CWSS algorithm, can dramatically overcome these real-world communication errors. It effectively makes those noisy reporting channels almost perfect for the purpose of spectrum sensing, statistically speaking.
Bringing the performance nearly back to the ideal error-free case.
The aha moment here, for me, is just how a seemingly simple concept, just repeating information, can be the key to unlocking the full potential of such complex cooperative systems.
Sometimes the simplest ideas are the most powerful.
It allows us to build more robust, more intelligent wireless networks that can truly adapt to real-world imperfections, the messy reality of the airwaves. It moves us closer to a truly dynamic and efficient shared spectrum.
So what does this all mean for you listening? This deep dive isn't just about obscure wireless protocols or complex algorithms for engineers. It's about the fundamental building blocks of future connectivity.
And how the unseen layers of technology profoundly impact your daily digital life.
Exactly. By making our airwaves more efficient, by making our devices smarter and more cooperative, and by finding clever ways to overcome real-world challenges like these reporting errors, research like this lays the groundwork for truly seamless, interruption-free wireless experiences.
In a world that's just becoming increasingly reliant on sharing that limited spectrum resource.
It promises a future where your devices don't just connect, but connect intelligently. They optimize their usage, finding the best available channels to give you the best possible experience.
Whether that's lightning-fast downloads, crystal-clear video calls, or perfectly reliable smart home automation, it's all underpinned by this kind of smart resource management.
Now, this paper showed how much improvement we can get with simple repetition codes. But it hints at more, doesn't it?
It does. It makes you wonder, What if we moved beyond simple repetition? The paper briefly mentions investigating more sophisticated channel coding techniques, or maybe burst error correction codes designed for situations where errors clump together, like during a long fade on the reporting channel.
Could that push spectrum sensing reliability even closer to near perfection? Or would the added complexity, the extra processing power needed for those advanced codes, start to outweigh the benefits, especially for simple low-power devices?
That's a great question. Is there a point of diminishing returns? And connecting this back to that initial sampling challenge we discussed, the problem of sensing the wideband efficiently in the first place.
Right, the PBNS versus full Nyquist or complex compressed sensing.
How might combining this robust RCCWSS approach for reporting with advanced sampling techniques, like maybe using compressed sensing to sample the partial band at the sub-Nyquist rate, truly revolutionize things?
Could that combination give us both efficient sensing and highly reliable cooperative reporting? Could it allow for unprecedented, truly dynamic, and efficient access to our shared wireless world, maybe enabling entirely new applications we can barely imagine today?
What do you think is the next big leap for our wireless future? And how might these unseen innovations in cooperation, sensing, and error correction continue to shape it?